thanks a lot to the hosts for having me here at PSAS. It's my first time, so very excited that I'm allowed to present on behalf of the MUMAS collaboration our latest results. So MUMAS, our main experiment, our main aim is to measure the muonium 1s-2s transition and to improve it. There was a poster from Irene Kortinovis about that, so I hope you had a chance to see it. In case not, I'm sure she's happy to explain even more. What I'm going to focus on is here the lamp shift transition in muonium, so the splitting between the 2s and 2p.5 state. Of course, it's not so simple, and we've seen this energy levels a lot of times. So here, for example, for the hydrogen atom, that we would have, due to the hyperfine structure, actually 4 transitions that would be allowed, 2 of them sharing the same resonance. So what we can do is actually scan 3 resonances to determine the lamp shift. And if we would have some contribution also from the finite size effect, so for example, in the hydrogen due to the proton, we would have to take that into account as well. Now, the nice thing about muonium is that we don't need to do that, because muonium is a bound system of a positively charged muon in the center and an electron orbiting around it. And since we consider both the electron and the muon to be point-like, that means that we don't have any of this finite size effect. This makes it an excellent candidate to probe bound state QED, because it's well, I would not say straightforward, but it's definitely simpler to calculate it than, for example, in the hydrogen atom. And it also means that when we compare our experimental values with the theory, any deviation that we would find might be a hint for new physics hidden there. There are already some interesting anomalies popping up in the muonic sectors, and we've seen already, for example, from Ben's talk about the G-2 for the muon. And you see, we would have this 4.2 sigma discrepancy if we look just at this white paper standard model. If we then look at the lattice QCD calculations, then it reduces a little bit, or quite a bit actually. So it might still be a motivation to study muonic systems a little bit further. But there is also another one, so the test of lepton universality, and just recently from LHCb measured from B mesons decaying into kaons and either electron-positron pairs or muon-antimuon pairs. And from the standard model, one would expect that the ratio between these decay channels would be the same. So the same amount of electron-positron pairs and muon-antimuon pairs produced. But they showed that this is actually not the case. There's an overproduction of electron-positron pairs. It is a 3.2 sigma, I think, discrepancy by now. So there's quite some hints that it's very interesting, not just for QED reasons, but also to look for new physics in muonic systems. Now, how do we produce our muonium? What we have is an incident beam of, we use a continuous beam of positively charged muons, and we let it interact with a target. In our case, we have a carbon foil installed in the beamline that is 10 nanometer thick. And this positively charged muon, this interacts with the carbon foil, it starts to straggle, it loses energy, it releases secondary electrons out of the foil, but it also has a chance in the end, after it lost some energy, to pick up an electron and continue its path as muonium. And there's even a fraction that is already prepared or is in the 2s metastable state. So we don't need any lasers or anything to induce 1s-2s transition to continue with the lamp shift measurement. We already have it in our beam. It's very important for this technique that you have the right initial conditions, because the more the beam straggles inside the carbon foil, also the more diffuse, the more scattered it comes out of the carbon foil. And that also means that we cannot use, since it's not so directed, we lose a lot along the beamline until the atoms reach our detectors. So what would be beneficial is to have here a rather low energetic muon beam and a really thin carbon foil to have a high yield of muonium and muonium in the 2s formed without having it too diffuse afterwards. And this, to find that in a beamline is quite tricky. I know about one, and this is very close from where we set up our experiments. So I'm working at ETH in Zurich, and we have close by at PSI, it's an hour drive, the LEM beamline. This is the low energy muon beamline. And this is exactly what we need for our experiment. It delivers around 5 to 10 kilohertz, a continuous beam of positively charged muons. And we can select an energy range between 2 to 20 keV, depending on the conditions that we can use and shoot onto this carbon foil. We did some tests, how efficiently do we form muonium. And you can see here, depending on the energy that we select, we have something between 20 to 50%, let's say. One can also see the lower energies we go, the statistics are not so good anymore. So that's why we have such large uncertainties here. So what we in the end settled for is some compromise, that we have high formation efficiency, but also good transportation efficiency to our detectors. We also looked at the formation efficiency of 2s, so how much of the muonium beam is actually in the 2s state. And what we see with our detectors is roughly around 10%, so it's a very good yield for us. So we started to construct a setup for measuring the lamp shift. Here, the first stage, I've already explained quite a bit with the carbon foil. An addition to that is that we use the electrons that are coming out of the carbon foil. We detect them with a microchannel plate, which gives us then the start time of the experiment. So we look at really on an event by event basis of the muon coming in, how long its flight path, how long is the time of flight for it. As I explained, we have already 2s in the beam, and both 1s and 2s are limited by the muon lifetime. So that's both are stable for me for a lifetime of 2.2 microseconds. So this is long enough for our time scales that we measure. And what we want then to do is we have these 2s entering our microwave region, and we apply this microwave transition around the gigahertz to populate the 2p½ state. And the 2p½ state, you see, is very short-lived, 1.6 nanoseconds. So it will relax back to the ground state under the emission of a Lyman alpha photon, so 121 nanometers roughly. In this region here, we just lose these Lyman alpha photons. We don't care too much about them. But the 2s atoms that haven't been affected by the microwave here, they will enter this Lyman alpha detection region. And there we apply an electrical field. So what we do is the 2s that we have, we do the Stark mixing, or in the jargon, electrical quenching. So we push these 2s also into 2p½ state due to the electrical field, which undergo then the same reaction. So go back to the ground state as well. And this time we actually care about these Lyman alpha photons. So we surrounded this entire Lyman alpha detection region with Lyman alpha detectors, which is just microchannel planes with a coating of cesium iodine or potassium bromide, which acts as a converter from a single photon to electron. And the electrons then are easy to detect with a microchannel plate. And then in the end, we have the beam going onto another MCP, which gives us the stop time. So we look for signals, additional signals in a certain time window, depending on the frequency that we apply. It would look something similar to that. So when we're very much off resonance, we still see a lot of 2s detected, a lot of Lyman alpha photons counted. And the more we go to some of the resonance, the lower and the lower the count rate gets. Now, since we really, well, it was the first time we set it up, so we had to make a lot of thoughts about it. We put quite a detailed simulation together. We profited already from the MUOSR simulation from the LEM beamline itself. So the beam profile that we get from the muons onto the carbon foil, this was already simulated and benchmarked, so we could use that. And based on that, we built we added our regions to the Giant4. The interaction with the carbon foil, this was already modeled as well in the MUOSR simulation. So the straggling, the energy loss, this was benchmarked as well. What we had to add is the muonium and the muonium 2s formation. Then the interaction with the microwave, there we were inspired by how Lundin and Pipkin did it for the hydrogen lamp shift. And also the microwave itself, so it's a transmission line, we basically copied their design. And then we also copied in the way how to simulate the field maps. So we used for that Simian. And we use these field maps then in Giant4 to simulate or to numerically solve the optical block equations for a two-level system. So like this, we can give a probability that this specific atom flying through this entire setup has to get into the 2p state and then go back to the ground state. This stage here for the electrical quenching, for optimizing our fields and the geometry, that we also have a large solid angle covered. For this, we used muon. And that's what's basically it. So we use it for optimizing to also study systematic effects. And in the end, we used it also for the line shape fitting itself. So to model our line shape. Now, as I explained, we can unfortunately not do that in our labs at ETH because we don't have a muon beam, but at PSI. So we need to grab our entire setup. We drive it to PSI and then we fly it into the experimental zone. And then for me as an experimentalist, this is quite some scary 4 or 5 minutes when you see your setup flying through the air. Really, really hoping that all the screws are tightened enough. So far, we never have any problems, and I hope we continue like that. Okay, we have it in the zone. We have a few hours to attach it to the beamline. We have a few days to gather statistics. Typically, I already mentioned it. We do time of flight measurements. So we, for example, look how long does it take an atom from the start to the stop. And this is what I plotted basically here, this distribution. And how long does it take? One can take, for example, here from the tagging to the Lyman alpha detector, which is this axis here. And we can identify like that, where do we expect our Lyman alpha? Where do we think our signal region is? And you can see we have quite a bit of other stuff here, but thanks that we have really a chance to cut it on an event by event basis, since we use a continuous beam, we can reject most of the background that we would have. Here we have a zone that I call A, which is consisting of events that were slightly too slow than what we would have expected, although we simulated. And this might be caused by, so when the muon is interacting with the carbon foil, there's also a chance that convoy electrons come out. And these convoy electrons, they have the same velocity as the muon. So not the same energy, but the same velocity. So what can happen is the muon actually hits back on the MCP, and the electron with the same velocity just goes up like that and gets detected by the cesium iodine detectors, because it's definitely deflected by the electrical field we apply. Which means that we could have some background here. We are not 100% sure yet if it's really that. With the B events, so they lie perfectly on this line, and I think we can already guess what it is. These detectors here, they lie very closely to each other. So when muons hit on here, there is a chance that they induce some noise also on the Lyman alpha detectors, which both are picked up at almost the same time, which we call crosstalk. So not really the traditional electronic crosstalk, but really induced by the MCP itself, which we can easily cut. The region here is even a little bit worse because our pulses are not super nicely shaped, just a single pulse and relaxing back to the baseline. But there's always some after ringing with some undershooting and overshooting, which can also be picked up by our discriminators and being an additional event since we record multiple events on the same MCP. So this would be this fraction back here. But in the end, with applying these cuts for the frequencies we apply on the microwave, we can then build our line shape. And that's what we obtained here. So this is for scanning these two orange transitions and the green one. Unfortunately, the blue transition from f equals 0 to f equals 1 is quite isolated. Well, unfortunately, just in this case, because our microwave was not broadband enough that we could scan such a broad frequency range. So we focused on these two for now. And yeah, with the line shape model, we fitted it. And you can see here, we get the statistical uncertainty of 2.3 megahertz, which roughly corresponds to a factor of 10, or an order of magnitude improvement to the previous measurements done in the 1990s. From the systematic effects, there is one that pops into the eye, which is the 4s contribution. So from the carbon foil, we don't only produce 2s, but we have also 3s contamination 4s. And there would be a 4s contribution just lying somewhere here, really tiny, but it is there. And we tried to include it in our line shape model, and the fitting disliked it, so our chi-square got worse. But we know that we have some percentage of 4s in there, so we forced some contribution on it, so we can estimate the actual systematic effect that we would introduce. And it's rather large. All the other ones, so that's, for example, the Doppler that we estimated, depending on the power, so the Stark that we maybe underestimated or overestimated, and so on and so on. It's very negligible to the statistical uncertainty. Compared to the theory that we also reviewed, just with the latest calculations for hydrogen, plus some additions for muonium, and of course, getting rid of the finite size effects, you see it agrees very well. And the result that we have here, of course, it's not yet there that we can actually say much about bound state QED that, for example, hydrogen hasn't been able to. But we can start constraining new physics for some muonic systems. Yes, this we already saw here. I just omit the lattice QCD corrections, and I assume just the one from the standard model prediction. And what we can look for is for a new fifth fundamental force that is unknown to this day. The main process for this G-2, you for sure all know, is this vertex correction here. And one could imagine a similar process of some unknown boson that interacts with muons with this coupling constant Gx that has a certain mass m. That would do a similar process. So one can add this additional boson to the theory for the G-2, and one gets a favorite region. So one combines the G-2 with the muon together with the electron, since with muonium we're sensitive to electron and muon. And we get this favorite region where such a new particle, such a new force would accept something like that to be. And what we can do is we do the same. We take this Yukawa type potential. We calculate the perturbation, we calculate the energy shift that one would expect if something like that is around. And we can plot then our curve with our uncertainty to say this would be still possible. So everything below this blue line we cannot probe. Whatever is intersecting, so this tiny area here, we can say from our measurement is not possible. Now you might say might not be so interesting, because with the 1s 2s measurement of muonium, this has already been checked and excluded. The interesting part for me, at least, is if we improve by another order of magnitude the Lamb shift measurement, we would get access to a new region that hasn't been probed by 1s 2s yet. With the final goal of mu mass with the 1s 2s, then of course, again, it was beaten. Another thing that we can look at is the standard model extension. So we take the standard model and we add some additional coefficients that would allow for either Lorentz or Lorentz and CPT violation, which would cause some additional energy shift as well. And what we can do here, also here we did an order of magnitude improvement. We can set an upper limit what these coefficients can be, because our result, everything above, is excluding. Now I promised you there's at least 3 resonances that we can observe, and I've only showed you 2 so far. So by changing slightly our microwave system, we got then also some power in this range. It's not so much interesting in the sense for determining the Lamb shift itself, because you see it's still statistically limited, and we're further off because it's harder to get large statistics just with this resonance. But it's exciting in the sense because nobody has ever observed this transition in muonium, so it's the first time. And also you see here this yellow contribution leaking in. So again, coming from beam contamination, there actually would be the n equals 3 Lamb shift line, so 3s to 3p.5, which is a little bit messing up our idea of seeing this isolated line, because when it's isolated, it's easier to model, less systematic effects. But actually, we can get rid of these contaminations. I will come to this later. But it's already an exciting first step. If we get enough statistics that we can actually go back to this transition, measure it accurately, we have less systematic effects and easier modeling to think about. Now, as a summary of everything we've done, you see here the first three measurements. It's a little bit tiny. The first three measurements of the muonium lamp shift with these huge or longer error bars because they were really limited by having not such a nice intense beam as we do. Then here is our result of the 2.5 megahertz. And here the result of this 6.8 megahertz from the f equals 0 to f equals 1 transition. Now, our goal would be, of course, we don't want to stop with 2.5 megahertz because we think with minor modifications we could go lower. I would hope for an order of magnitude improvement as well, which would allow us to probe, as I mentioned, this favored region for the G-2 for this new unknown force. Also further probing SME, of course. And we would also start getting sensitive to some contributions to the theory that hydrogen hasn't been able or hasn't reached yet. For example, here, this is the Barker-Glover term. This is all relativistic recoil corrections that we are more sensitive to with muonium because the nucleus is 9 times lighter, so less weight, which means, for example, the Barker-Glover is inversely proportional to the power of 2, which means 81 times more sensitive than in hydrogen. So around 160 kilohertz, this correction lies. So once we reach there, and we would be able to tell something about more corrections as well. And I think we can reach that with a few minor modifications. We definitely need to get rid of our beam contamination because this is hard to model and this we definitely don't want to. We can do that with a weak electrical field just after the production. This is, for example, what Eric Hessels does to get rid most of the contamination he would have, leaving the 2s almost unaffected. So most of the statistics we should still be able to gather. And then we would also like to change our formation targets. So I said we have 10 nanometer foil. There are some applications that they used already 1-2 nanometer foils, which would mean that we would have less straggling, so more directed beam, and therefore we estimate it should be factor 15 to 25 alone by just changing the target. And then we would have to, the data I showed was 2 days of data collection, so if we would do that for 10 days, which is usually the beam time that we apply for, we could reach actually some order of magnitude. If we want to go further down, then we need more upgrades, for example, mucool that Ben has already talked about as well, or the HIMP upgrade. With mucool, we could then probably also change not just carbon foil targets, but also gas cells where we could produce our muonium, which would even be better. HIMP upgrade, we would get much higher flux of incoming muons, which would help us greatly also then to be able to study systematics during the beam time itself when we are capable of collecting enough data within few days. I hope I still have some time because I'm also part of, or our group is also part of the GBAR collaboration. And of course, this system that I show here is not only limited to muonium. We use it with hydrogen, for example, to characterize, to study the systematics. The same can also be done with antihydrogen. Nothing prevents you from that. The only part that needs to change is the formation. And the idea of GBAR is that we use the antiprotons coming from the Elena storage ring, which are roughly at 100 keV. We have to still decelerate them down to around 6 keV. And then it interacts with a positronium cloud. So there's a pulsed positron beam shooting onto a silicon oxide target, forming a dense cloud of positronium, which we synchronize together with the antiprotons. And then you have a good or a chance to form antihydrogen and already also a fraction in the 2s state, which would mean we could do pretty much the same experiment just with antihydrogen. Now the setups, they have been tested. Here you see, for example, a line shape that we took at PSI with protons on a carbon foil. Here you see also again beam contamination from the 4s. This will not be a problem for GBAR because the beam line that we have there is just much longer. So just from lifetime, they will depopulate way below. The setups, both microwave here and the Lyman alpha detection setup, where we commissioned them with protons and the carbon foil. Also at GBAR now, we have a carbon foil and the proton gun. So when there's no anti-protons, we can further characterize and check the systematics. Currently, we're waiting for antihydrogen. This is the most, for sure, the most difficult part of the experiment. They are currently anti-protons being ejected to GBAR, and the mixing is being tried, but of course it's not straightforward. So we're waiting for that currently. Yeah, that was it from me. Thanks a lot for your attention.
Thank you, Gianluca. So, are there questions? Yes, Frederick.
A technical question: when you have these electrons that you entrain with you and they go to this Lyman alpha detector, you could reject them by putting a negative potential in front of the Lyman alpha detector?
Yes, yes. Actually, the first attempts we did for detecting Lyman alpha, we actually did that because electrons as a background is always a little bit of an issue. But we see, so when you have the coating is on mainly on the top layer of the MCP and goes a little bit into the channels. But if you repel the electrons basically coming in, then you lower your detection efficiency, which because whenever an electron is formed on the front plate of the MCP, you need to somehow force it to go into the channels. And by applying there an electrical field, you would probably you do squish it away, let's say.
But then you put two grids.
Another grid in front, yeah, we could do that. We have actually 2 grids there just for the quenching. We should definitely try this.
So, other questions? Yes. You've shown SME limits with the unit inverse energy to the 3rd power. So this is dimension 8. How about the lower order SME corrections? And can you comment on the time resolution of your data and on some efforts to do some time-based analysis on these results?
Unfortunately, I'm not much of an expert from SME, so I can say we do usually have beam times in December, and this data was taken in June, so we could do something like that. But large statistic, the 2.5 megahertz was only taken in June. We have probably from December something like 7-8 megahertz measurement that we've never shown. One could do it, but for now with these uncertainties, I guess we're not very much sensitive to anything. From the unit.
Again, how long does it take to sample one line in your case?
So this line here that we were showing is roughly 2 days of data taking. Yeah.
Thanks. Yes, Dave, please, and then Nancy afterwards.
Maybe you don't know this, but is the production of the states that you don't want, the 4 and 3, does that depend on the thickness of the target?
That's a very good question. I wouldn't think so, because usually this formation really happens only at the end of your target. So really like at the last layers. Probably it happens a lot of time in your target, and only in the last layers it manages to keep, let's say, the electron with it. I am not 100% sure, but I wouldn't think so. But I haven't seen data about it. So there's very sparse data, even for hydrogen. So protons on foils. We had a hard time to get everything together, and usually it's just relative ratios, never like absolute ones are super hard to get. So yeah, I don't have any conclusive.
We respect it really at the surface. Nancy?
Yeah, so this is also a question related to these complicated line shapes with many contributions. You talked about chi-squared. Have you used Bayesian analysis techniques to try to, where you can quantitatively compare different models? So have a number of peaks would be in your case?
No, we didn't use any Bayesian method, no.
It might help.
It's very good input, thanks.
Yes.
Okay,
yes,
thanks for the very nice talk. I have a question about the 5th force. Could you go back to that slide? Yeah. Okay. It seems that the lamp shift is not converged in the low mass. What's the reason? And yeah, if I understand other lines correctly, it's the product of this G-2 electron and a neutron, right?
Yes, yes,
Yeah.
it's the product of both. Yeah, that's a very good question. Actually, we discussed that even at PSAS here with having a few beers. Well, eventually what you do is you just take the hydrogen wave functions and you get the expectation values. So the difference between 1s2s and 2s2p is that in one you have still the circular shape, and where the other one you have. But intuitively, I mean, we came up with the idea that the shorter masses you have, the shorter range you're gonna have. So since the overlap of the wave function and the 2p is complete, or in the center with the muon is completely different. But really a good, maybe Ben comment on that, because maybe Mike too.
Gianluca said it, but just to reiterate, when the mass goes to zero, the force is like a Coulomb force, but with a different coupling. And this is a non-relativistic framework. There's no lamp shift Coulomb force in a non-relativistic framework up to second order mass correction. 2s2p cannot discriminate force that's not carried with something that has zero mass.